Whoops. Alright, there we go. Hello out there. Let's see, as far as YouTube is concerned, we have one person watching so far, so let's see how it goes. Looks like I unintentionally lost track of what time the clock was saying, so getting a little later start than I intended, but pretty typical for me, I think. Alright, got a couple more people in there. Oh yeah, go ahead and chime in. Let me know you're out there. There's a lot of green dots in the Discord, so I want to wait a little bit to see if more people are coming before we really get started. Let's see. I'll send one more at everyone here just to get people's attention if they want to watch live. So all right, so yeah, okay, counter's up to 5, so I think people are popping in a little bit. I need to go grab my soda. And so I didn't see too many, if any. Let's see, are there any questions over here about Lab 7 that I have not yet addressed? Let's see. Okay, well, there's one good question. I'm pretty sure there's a file read function in Java that you can just read an entire file into a string. If that doesn't work, you just read it in pieces and concatenate them together. At any rate, I suspect that that will be easy enough to resolve that I can answer that question offline. But I'll just put it out there while we're live now. For those of you that are here, any questions, any other questions on Lab 7? And if you have them, go ahead and jump over to the Lab 7 channel and pop them in there. I'm going to stay in general unless I see Lab 7 channel light up. But I imagine you would have asked, if you had a question already, you would have put it in there. So, I think I will go ahead and get started on what we're going to be talking about tonight. So, last week we talked about graphs and got through quite a number of concepts related to graphs, but we didn't really get into any practical nitty-gritty of what you would do if you were writing algorithms or programs that work with graphs. And so that should be the focus today, as well as talking about the traveling salesman problem. I also do want to spend a little time. I don't think I really talked about this maximal flow problem, and I think that's a pretty interesting problem conceptually. So, or did I? Can you remind me if I talked about maximal flow very much? So I sort of vaguely remember mentioning it, but it might have been just like really briefly. So if you recall me talking about it significantly, let me know and I can avoid diving too deep into that. Let's see. In fact, I think I'll just go ahead and save that for now. I know the textbook talks about the cut set problems, so you will get some information about that just from the textbook. Yeah, I did. The directed acyclic graph. Oh yes, I did talk about it in quite a bit of detail. Now that you remind me of the diagram and I look at it, yeah, because I talked about okay, like the numbers associated with each edge. You can think of those as something like a pipe capacity or something like that, and then you can associate another number, which would be how much water or whatever flowing through that pipe. And the idea here is you have sources which only have outgoing edges, and you have sinks which only have incoming edges. And the problem would be to figure out what is the maximum possible flow from the sources to sinks. And that turns out to be equivalent to finding some set of edges that you could cut the graph into two pieces, basically separate the sources from the sinks by cutting. And I don't think I mentioned this aspect of it. So let me use red for that. I'll use blue for this. So there's going to be some bottleneck here. Like maybe it's these edges. Like if we cut all the edges that I crossed with this blue line, maybe cutting those edges out and totaling up the amount of flow on those edges will tell us what the maximum possible flow is, or something like that. Or maybe that's not the bottleneck. I think actually the bottleneck is up higher. I think the bottleneck's up here somewhere, something like that. But at any rate, the maximal flow problem is very similar to what's called the minimal cut set problem, where you divide your graph into two parts, and there might be conditions on what the two parts have to be. Like here, its sources and sinks have to be separated. Other cut set problems, it may just anything that separates the graph into two non-empty sets of nodes might be all you're looking for, or you might have some requirement about how the nodes are separated, and then what's the bottleneck or the minimum set of edges you can yank out of the graph to split the graph in two, which is a very that's a very important, just as an abstract idea. That problem crops up in any kind of situation of logistics or network routing and so forth where bottlenecks come in. So that's a pretty interesting problem, but it's not, we only have so much time, so we're not going to dive into a lot of detail on that. But I did want to make sure that I discussed it. So it sounds like I actually did cover that in enough detail, so we can move on and talk about graph representations here. And that looks like I'm crossing it out, and I don't mean to cross it out. If anything, I should bold it to make it clear that's what we're talking about now. All right, so I think this is going to be more worthwhile before I talk about the traveling salesman problem. That's the one you're actually going to be doing work on, but we might as well see how we can represent graphs in an algorithm in a computer program, and which way we probably want to do it for this problem. So the textbook gives you a fair amount of discussion on adjacency lists, and I might have to look closer, but I think it does not delve as deeply into adjacency or cost matrices, but that's the one I would suggest you use for this problem. But at any rate, an adjacency list just means pretty much you would set up your graph data structure. You would define a class that represents your vertex, a vertex in your graph, and whatever information you need. I mean, you might have a label that is a string, or a label that is a number, or both. You might have other information about each vertex that would probably depend on the very practical problem that you're writing a program that was dealing with graphs for. So if you're talking about routers on the internet and your nodes or your vertices in the graph represent internet routers, then you would have all kinds of information about the performance, etc., of your routers, and even like the make and model, and who knows what information you'd want to keep track of. But from the graph theoretical point of view, we just need to know it's a vertex. It needs a label of some kind, maybe an index. And then you also need to know what is it connected to. And so one of the member variables of your class would just be a list of all the other vertex objects that represent the vertices that it's connected to. So that's it in a nutshell. That's an adjacency list. Definitely read what the textbook has to say about those. You might decide that adjacency lists make more sense to you and you want to try and write the traveling salesman problem using adjacency lists. But I do think the cost matrix is probably going to be the way to go. What else do I want to say about adjacency lists? The one thing I think that can be an issue with adjacency lists is keeping them consistent, because if you have A connected to B, if B is in A's adjacency list, then A should also be in B's adjacency list. And those are two separate lists that have to be maintained, but the information in those two lists has to be kept consistent in some way. So that's where, adjacency lists can make programming stuff relating to graphs a little bit more of a headache. It's not as big a deal if it's a directed graph, if the if you can have arrows in your graph, like we looked at with the DAC here. If your edges are basically arrows, then you probably want to set your lists up to represent a list of everything that I'm pointing to, and maybe you don't keep a list of things that are pointing to me, so to speak. So if you think of the node as you, like if this node is you, so to speak, if I can get one to highlight without everything else being highlighted. So if that node is you, then maybe you just want to keep a list of everything that you are pointing to, so to speak, everything that you have outgoing edges that lead to, and you don't try to maintain a list of incoming edges. You don't have that consistency problem, but you do have a little bit of a problem of, well, if you have an algorithm and you need to know what is pointing to that node, if you're looking at that node and you want to know what's pointing to that node, you have no direct way of finding the things that point to that node. Unless you keep an adjacency list of the things that are pointing to it, as well as the things that it's pointing to, so to speak. So adjacency lists create some headaches, but if you have a very sparse graph with not a huge number of edges relative to the nodes, adjacency lists might still be more practical, because the alternative is what I'm going to talk about now, which is the adjacency or cost matrix. So an adjacency matrix is simply a matrix of ones and zeros, where a 1 represents an edge and a 0 represents no edge. So actually I should probably throw that in here. So you represent your adjacency matrix, which is the simplest sort. So you have a 0, 1 representing edge or no edge. That makes it very easy, because all you have, if each node has a number from 0 to n minus 1, then you just have two indexes into this two-dimensional array, and you look up to see whether they're connected or not. So you don't have to maintain a list. You don't have to worry about consistency. Well, there's one minor issue of consistency that does come up with the adjacency matrices. if you have a non-directional or a actually I should probably phrase that as non-directed. If you have a non-directed graph or an undirected graph, then connections go both ways. So you have to make sure that the matrix is what's called symmetric. Let me phrase it this way: adjacency ij should equal adjacency ji for undirected graphs. For directed graphs, ij represents one direction, and then ji represents the other direction. So they don't have to be the same, since it may not have both directions between any pair of nodes, and you may not. But there might be some adjacency graphs where, for example, directed acyclic graphs, you can't go back. You're not allowed to go back. In which case, one of those two would have to be 0. And the other one would represent an actual direction that you can go, or possibly both can be 0. So I think that's fairly straightforward, but we might as well make a concrete example. So let me grab the graph that we have from up here, see how much of it I can get without dragging too much stuff along. Oh, of course. This is one note, so I have to do that. All right, good. And maybe oops. I know. Zooming in, that will help. Get rid of some of this stuff. All right, how is it erasing that circle before it erases the green stuff? Tell me. There we go. All right, I'm just going to leave some green stuff because you shouldn't have to sit there watching me mess with this too much. All right, so let's see. Don't need this little text box. So this is our an example graph. We have some things that are not connected. We have costs associated with some edges. It looks like I've lost some of those costs. Let's go ahead and put new costs in. I don't know, we'll put a 5 by that edge and a 13 by this edge and a 4.6 by this edge. Okay, so an adjacency matrix, we would want to create a 7 by 7, but I need headers and labels, so I'm going to go 8 by 8 here. And let's see, it'll let me shrink that down at all. Nope. So it won't look very square here, but oh wait, I've got 8. I wanted 9. Darn it. So table, insert right, table, insert below. All right, there we go. 1, 2, 3, 4, 5, 6, 7, 8. Oops, don't want the 8 there. 0, 1, 2, 3, 4, 5, 6, 7. And if we look at our diagram over here, okay, 0 and 1 are connected. So we would want a 1 there for an adjacency. 1 and 2 are connected, so we would have a, well, let's stick with 0. So 0 and 1, 0 and 4. Everything else is not connected, so we'd have a 1 there. And just to make it a little bit more readable, I think oops, come on. There we go. So it's a bit more readable. I'm just going to leave the zeros blank. So we'll just have the 1s there where we actually have a connection. So we have 1s there and there. So that's 0. And this is not a directed graph, so the column has to match the row. So the 0 row and 0 column should be the same. So we should have a 1 here and a 1 here. And those are the only two things node 0 is connected to. So let's go on to node 1. 1 is connected to 0, that's already there, and 3 and 2, so we should have a 1 here and a 1 here, and nowhere else. Oh wait, nope, 1 is also connected to 7, so we should have a 1 there. 2 is connected to 1 and 6, so we've already got the connection with 1, but not the 6. Well, we don't have it listed in 2's row. We have it in 1's row, but we don't have it in 1's column or 2's row, so we need that one. And again, we want the rows, each row to match the corresponding column. So if we go down this column, we should also have 1 there and 1 there. Actually, I think I'm going to leave these blank for the moment. And let's see if it'll let me do this. Need a different shading color, so let's go yellow, why not? Then table shading, and so on and so forth. Voila. Okay, and anybody watching in video is probably wise and knows to skip over when I do boring stuff like that. Okay, so at any rate, we have one triangle highlighted there. Might as well get this one down, the lower triangle down here. And what would be a good color for that? I guess blue. Oop. Wait, you know what? I think if I do that. Nope. Darn it. Oops. What did I just click on that? Oh, good grief. Convert to spreadsheet. No, 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 no. No, no, no. Okay, there, that's a little better. All right, so let's just focus on this upper right triangle here. So, so we were on 0, 1, 2, and I apologize, this is probably a little obvious how this works. So 2 is connected to 6. We only have to consider nodes of higher numbers when we're looking at the yellow triangle here. So 3 connected to 4 and 6. 4 is connected to 5 and 7. Looks like. And 5 is only connected to 4. 6 is connected to 7. So we have a 1 there. All right, so if I didn't miss any, I've got all the edges marked in here as 1s. Again, just treat blanks as 0. That if we don't put the zeros in, it just makes the 1s stand out better visually. So I think it's easier to look at if we just put 1s in and leave the zeros blank. Now there's two things you could do. One is you could always kind of make sure your code is designed to work only with one triangle out of the matrix, but generally most programming languages, you're going to define a 2D array. You're going to have all this memory get used for this half of the array. Anyway, you might as well have it filled in and just be able to use either one. But you do then need to make sure that if it's an undirected graph, that you keep it consistent. So the 0 column should be the same as the 0 row, so we should have 1 there, 1 there, 1, 1, and 1 down there, a 1 on the 6th row, a 1 here and here, and a 1 here and here, and a 1 here. And that takes care of it. And of course, the diagonal is a node to itself, which most graphs, well, I guess depending on the problem you're going to deal with, you might have self-links. Self-edges may or may not be a thing depending on the graph problem that you're solving. Most graph applications, most kinds of graphs we think about do not have self-links. It's not very meaningful. But certainly there can be situations where you do want to have self-links. If you studied finite automata in a discrete math class or a math for computer science type class, finite automata certainly have self-edges. You can go from each node is a state, and the edges represent transitions from one state to another, and you can have a transition from a state to itself, which would correspond to one of these diagonal cells in this 2D array. But for most problems, you're probably going to be looking at something like this. Now, if you have a directed graph, so if we went to one of these, where each edge is basically an arrow, then we would want to allow these two halves of the matrix could be completely different. And depending on the rules for your directed graph, like if you can only have one-way connections, then you might say, well, if I have a connection from 2 to 6, okay, so the yellow would be 2. I'm going to put this up in the note temporarily. So if the yellow was our to direction, then the blue would represent from, right? Actually, that's not. Let's think of it this way. Let's say our rows are I and our columns are J here. Whoops, went one step too far there. There we go. So these across the top consider to be J. These going down consider to be I. and we'll say this is from I to J, right? And down here, let's call this from J to I, if directed graph. And so this is applicable if directed graph. And of course, if it's undirected, then you should match. One triangle should be the mirror image of the other triangle if it's undirected. So keep that in mind when you're writing your algorithms relating to working with graphs. That you either need to flip your indices so that like always the lower index comes first. Always use the smaller index as I. That way you just only use one of these two triangles. But it's probably easier to just set it up so that when you first create it, just always make sure that the matrix element ij is equal to the matrix element ji, and you should be good to go. We're not going to be doing algorithms where you modify the graph. So if you just make sure it's set up correctly initially, then you don't have to worry about it. Then you're just going to be looking up the information in the graph at that point. So that's an adjacency graph. Pretty straightforward. Let's see if it'll let me get text above this. Yeah. I just do it this way. So this is an adjacency matrix here. And so let's go ahead. I can just copy this now. And let's take a look at a cost matrix. Oops. Let's jump up there in the text. So let's give myself a little more room. There we go. So, cost matrix. Oh, you know what happened there? I didn't keep the formatting. There we go. All right, now. OneNote is really handy, but a little frustrating sometimes. Okay, here we go. Cost matrix. Okay. So at any rate, here's the cost matrix. We just replace all the ones with the costs or distances along each edge. So here we have 1.6 kilometers going from 0 to 1. So we would put a 1.6 there. And also since this does not have direction to it, 1.6 both ways. Now, if this represented plane tickets, and for a variety of reasons, maybe this represents the monetary cost of plane tickets instead of distance, or something like that. There are many reasons why going one direction is cheaper than going the other direction. You know, either because you're going with or against the jet stream from LA to New York or vice versa, or because there's more demand for one direction than the other, whatever the reason might be. There could be many reasons why you could have a directed graph for a situation like this, and you could even, we'll be looking at the traveling salesman problem on an undirected graph, but you can easily see that the same problem could apply to a directed graph. But at any rate, whatever the numbers are, we just need to fill them in. So let's just stick with the 0. So the 0 to 4, that's a 99.9 there. And then coming across, 1 to 2 is 4.8. And 1 to 3 is just 4. And then 1 to 7 is 88, and so on. So 2 to 6 is 13. 3 to 4 is 2. 326 does not have a number on it in the diagram, so we need to make up a number. Let's say, I don't know. Do I have a 42 in there? We gotta have a 42 somewhere, right? Let's put a 42 in there. Okay, that one will be 42. So 326 should be 42. 324 is 2. That's already in there. Okay. All right. So 425 is, as it happens, 5 by coincidence. And here we have a 0.1 for 4 to 7, and for 6 to 7 we have a 4.6. All right, so that's all the distances there. And again, since it's the same both directions, we need to make sure that the blue triangle matches the yellow triangle. So there's a 4.8. There's a 4. There's our 99.9, and so on and so forth. There's a 2. There's a 5. There's our 42. There is our 13 and our 88 and our 0.1 and finally 4.6. And so now we have a cost matrix. Again, you just have to just be careful when you're programming these things that you keep it straight. Flip your I and J when you're building the matrix. Just if you're putting something in box IJ, then also put the same thing in box JI, unless you're working with a directed graph, which you shouldn't have to do. So if you keep that straight, then it doesn't matter whether you look up box IJ or JI later, because the correct number will be in both boxes. So that's a cost matrix, except there's one issue here. So here's let me just put this out for you to think about a little bit. So if we have no connection from 0 to 5, for example, so from this node up here to that node down there, from node 0 to node 5, we have no connection at all. So do we want to say that that's a cost of 0 from node 0 to node 5? Think about that and tell me what you think. Should that have a cost of 0? Right. Excellent. So if you think about it, well, just think about if you were trying to find a shortest path from 0 to 5. If we called that a cost of 0, then the shortest path would be that 0 cost path, right? So, well, if we called it a distance of 0, if these were distances, so, but least distance, least cost, whatever you want to call it. If you're looking for the minimum cost path, calling this 0 is definitely going to be an issue. So you probably want to consider it infinite, right? Now, as a practical matter, most programming languages don't just give you an infinite option as the values of your numeric variables. There are some languages that do. And I'm sure there's, even in Java, there's third-party libraries at the very least out there that probably give you a special, define a numeric type for you that lets you do infinite, positive infinity, negative infinity, things like that. But generally speaking, if you're just using plain ordinary integers or long integers or whatever in Java or C or C++ or something like that, you have to decide how to represent your infinity, and you have to make sure your program recognizes your choice for what means infinity. Maybe you use maxint to mean infinity, but you always have to then have an if my number is maxint, do something special with it. You can't just treat it like a normal number. But you have to make some kind of decision. In a situation where only positive numbers or zero makes sense, such as for distances or costs or something, I guess a negative cost could be real in an economic network of some kind, because that would represent money coming to you for some reason. So you might, negative cost might be valid in some situations, in which case you need a different way to represent infinity. You might just have to make up your own class and just have a special, a separate field. You have a numeric field for the numeric value, and then a separate Boolean field is true, false, is this infinity or undefined or something like that. And then you work with your class, and you don't work with just plain ordinary numbers. Whatever you choose to do, you have to write your program to recognize whatever you choose to mean by infinity. So, for example, we might want to go, writing it into a diagram, a table like this, we might want to just say INF, INF, INF. And that's a whole lot of them to fill in. I think I'll only do this half. So we have all these infinities in there. So for costs, how to represent infinite cost or no connection. So you have a variety of options. Make this a matrix of a small class and use a separate class variable to represent infinite or undefined or not connected. Something like that, separate from the cost, a separate variable from the cost or distance value. I think that's actually probably overcomplicated, so actually I should make this bullet points or something. Let's see. So you could do it that way. Let's see, if valid values are greater than or equal to 0, then -1 can mean infinite or not connected. So you got to do something to deal with the possibility that things are not connected in your cost matrices. But another option would be to have separate cost and adjacency matrices. I should say separate and parallel cost and adjacency matrices for the same graph. So we could have both of these matrices. You could have this one telling you whether the connection exists, and if it exists, this one tells you the cost, and if it doesn't exist, then you just ignore what is in the cells of the cost matrix where there is no connection. That effectively represents infinite cost. But that kind of doubles your memory requirements. You have to manage both adjacency matrices, or both matrices, the adjacency and the cost matrix. And for the most part, a cost matrix should be giving you all the information in the adjacency matrix plus the additional information of the cost, so that you don't really need an adjacency matrix. If you have a way of representing infinite or disconnected in your cost matrix, then you should not need an extra adjacency matrix. You can just use the cost matrix and forget about the adjacency matrix. So hopefully this isn't too obvious and everything, that it's at least worth a while walking through this a little bit, just to make sure we're all on the same page, if nothing else, about how to just actually physically represent, when you get down to writing code, how are you actually going to represent your graph. And I would definitely suggest taking the approach of an adjacency matrix, but I'm not going to force that on you if for some reason you feel like an adjacency list works better for the approach you want to take for something. Now let's see. Yeah, I think that's probably all I need to say about graph representations. So let's move on and actually start talking about the traveling salesman problem. Okay, so I think some of you have heard of this problem before and maybe looked at it a little bit in another class, but now you're actually going to write code to solve this problem, and as we usually do, you'll write 2 or 3 different algorithms that solve it in different ways with different performance characteristics, and you'll be running experiments to see how those work out. So let's see, I need to, actually I'm out of soda, so I need to pour myself a lemonade or something, so quick break and then I'll be right back. All right, let's see. So first we should start with a statement of the problem. So let's jump back to this page of notes. So given a graph G with costs associated with each edge, find a path that visits each vertex exactly once, returning to the initial vertex that has the minimum cost. Let me just make it absolutely clear, the minimum path cost. So the idea behind this is, if you imagine a salesman or a salesperson, as the case may be, they have to go out and they have to, visit some set of cities. They have to visit clients or whatever whatever they're doing to sell their wares. They have to visit a bunch of different cities. And so, of course, there's either travel distance or travel costs from one city to the next, which might just be based on how far it is, or it might be plane ticket costs, whatever it happens to be. And you want to minimize the cost of your sales trip. So you're going to visit all these places, and you want to minimize the cost of visiting all those and ultimately getting back home. And for the simplest version of this problem, the cost is always the same. So we're not worrying about, sometimes the airlines run a sale, and then, so for these few days, it's cheaper to go from city B to city D, but on different other days, it's more expensive to go from city B to city D, or, we're not worrying about quite that level of detail. That would be a whole layer of complexity on top of the basic salesman problem, traveling salesman problem. But this is enough. This problem is hard enough to solve. Let's put it that way. Well, in a way, it's very easy to solve. It's hard to solve quickly. That's what's difficult. So again, your idea is you want to visit all the cities where you have to make sales visits and come home. And of course, being a salesman and running a business, you want to maximize your profits, so you minimize costs. So of course, you want to take the route that is cheapest, shortest distance, whatever makes it the least cost path to you. That's what you want to do. The rule that you cannot visit the same city twice is not terribly important. You could come up with weird graphs where visiting the same city twice, the same vertex twice, actually gave you a shorter path. But that would be kind of an unnatural situation. Certainly that would be a generalized problem. Maybe since there probably are graphs where visiting the same city twice could even give you a shorter path, that would be what we call a generalization of the problem. And I'm sure people have studied that version of the problem. We're not going to worry about that version of the problem. It's an interesting enough problem just with the basic form of the problem. But actually that makes me think, and so I'm going to go off on a little bit of a tangent. Whenever we're looking at these problems, whether it's traveling salesman or maximum flow or whatever, there's always ways you can take, kind of the quintessential version of the problem, the most basic version of the problem, and come up with ideas or what are called generalizations of that problem, where you more or less you either add constraints or you free up constraints. So the typical traveling salesman problem, as I mentioned, is you visit each vertex exactly once. So you don't go back to a city you've already been to. But in the real world, going back to a city you've already been to might be the way to get the cheapest airline tickets. Who knows? So that's not necessary. There's nothing that says this has to be the constraint, but if you take away that constraint on the problem, then you're solving a clearly very related problem, but not exactly the same problem. So a path that visits every vertex for minimum cost is not necessarily the same as the path that visits each vertex only once and has the minimum cost for that requirement. And there could be other things. Again, you could take traveling salesman on an undirected graph, or, again, if we're talking airline tickets, which direction you go could change the price. So you may be looking at a directed graph, and then the number of possible paths explodes, because going from A to B is very different from going from B to A, or at least potentially quite different. So reversing your path or part of your path makes for a completely different journey. So it becomes a different problem again, a related problem, but still a different problem. So that's always something to think about. So if you go on and get deeper into computer science, go on to computer science graduate studies, things like that, when you start talking about these different kinds of computational problems, graph problems, and so forth, one of the things you can do to do something new, do new and interesting research, is to come up with a generalization on a problem that's already been studied. So, okay, the traveling salesman problem has been studied to death, but what about the traveling salesman on directed graphs? What about traveling salesman where you can visit vertices more than once, and so on and so forth? Now, not that I've actually looked it up myself, but I would just about guarantee that those variations have been studied to death as well, and many other variations on the traveling salesman, because this problem goes way back. People were studying this back in the 50s and 60s, and maybe they were even studying it before computer science was a thing, because it's kind of a logistics issue. It's something that mattered. Even people who traveled on foot, a few hundred years ago, have to visit several places. You want to do that as efficiently as possible. So this problem has technically existed since ancient times, I suppose you could say. Maybe not quite phrased in exactly the same way, but you get the idea. It's definitely something that mathematicians and computer scientists have been thinking about a long time, and so many variations of it they've also been thinking about. But if you do get into any kind of computer science algorithm research or something, definitely that's kind of the way to go. Is you see a problem that's been studied, you can always come up with a different angle, a different twist on that problem that may not have been studied so much, or maybe nobody's studied it, and then you write the algorithm that solves that, you publish a paper, and you go to a conference and present your paper, or whatever. But at any rate, traveling salesman problem. This is the essence of the problem. It's pretty straightforward. But let's go ahead and look at our example graph here, and let's just take a look by eye and say, well, what would the solution to the traveling salesman problem be here? One thing I'll tell you right off, which may not immediately be obvious, but if you think about it, it becomes obvious, is that it doesn't matter where you start. Because if you're going to make a loop, like if I start at 0 and find the shortest path that visits everything, and exactly once, which actually with this graph I just noticed is impossible, so we should probably add a couple edges to this graph as an example. But if we start at 0, visit every node, and come back to 0, and that's the shortest possible path that could do that, well, that's exactly the same as a path that started at 1 and gets back to 1. And it's the same as a path that started at 2 and gets back to 2. So if you could go and start at 1 and do some loop through all the nodes and get back to 1 and find a shorter route that started at 1, well, that route includes 0. So I could just do the same route starting at 0. So it's going to still be the minimum route. So that's not quite a formal proof, but hopefully you follow the logic there. It doesn't really matter which one you start. If you find the shortest path that starts at one node, that's also the shortest path through all the nodes that starts at any of the other nodes. So you can consider any of the nodes to be your starting and ending node, so it might as well be node 0. So now we have to find the shortest path that visits everything exactly once. Well, we do have a problem here where we have one node that's impossible because there's only one connection to it. So either this is not going to be a valid graph for our purposes, or we have to add some edges to it. Or we have to loosen the constraint. We have to say, oh, well, okay, if you're forced to visit one node twice, then I guess you have to. But we don't want to add those extra complexities. You're going to have enough work writing the programs to do this, so we don't want to deal with those extra complexities. So what I will say is when you get to the lab and start doing experiments, you should work with fully connected work with fully connected graphs, or at least have 2 edges out of every node. You may, if you randomly create graphs that don't have every edge in there, you could create a graph where the problem is unsolvable. And that might be what your algorithm has to answer, is that this problem cannot be solved. But let's go ahead and change our example graph here. I think I'm going to see if I can grab it and copy it to a new page. And somehow I just made things go wonky there. Okay. Did that get everything? I think so. Copy and paste. All right. And get the formatting. There we go. All right. So this is our graph, except we want to add some edges just so we actually have a solution that is valid under the rules that we're working with. So let's go ahead and throw an edge here and an edge here, and I'm not going to go fix the colors, so please forgive me for having bad colors. I don't know, let's go 12 as the cost of this edge, and 20 as the cost of that edge. Okay, and any edge that's not in there can be considered infinite cost. So as soon as you hit an infinite cost edge, you either say it's not connected, or it's just, it can't be part of the solution, unless you're forced to go. Like if we didn't just add these 2 edges in, you might conclude that you're forced to take at least one infinite edge, and so the best solution has infinite cost, or you're basically coming back with the result that it's impossible because you don't have enough edges to even form a cyclic path that goes through all the nodes. But at any rate, with this, it's pretty clear we can go from 0 to 1, 1 to 2, 2 to 6, 6 to 3, 3 to 4, 4 to 7, 7 to 5, and 5 back to 0. So there's at least one path in there, and I suspect there's quite a few more. Maybe not. It might be difficult with this graph to yeah, I think it might be a little difficult with this graph because I don't have enough edges. So again, one of the things when we're testing, when you're running your algorithms and testing, you generally are going to want to be working with complete graphs or near complete graphs, so that you're pretty much guaranteed that you have an interesting graph to solve this problem on. I'm going to add a few, what look, at least on this diagram, these look like long distance connections around the outside a little bit. But I'm going to hesitate to put any numbers on them. I think it's getting a little bit cluttered. So at any rate, let's just highlight a path that goes through everything here, right? So like I said, we can go from 0 to 1. I'm not going to do the one that I just announced. Let's go from, let's see, 3, 4, over to 6, up to 2, around to 7, to 5, and back to 0. So that's a possible path. So what is its distance? We have 1.6 plus 4 plus 2, so that's 7.6. We've got one here that I didn't put a number on yet, so let's go ahead and add a number to that one. Let's just put 10 on that one. It's a little bit hard to see what numbers go with what edges here because it's starting to get a little cluttered. This is where the adjacency matrix clears that up a little bit. And can I even get in here? Oh well, not going to try. All right, so let's say that one's 10. So we've got 1.6 plus 4 plus 2 plus 10 plus 13. So that's 23, 29, 30.6. Let's go ahead and give a distance on something here. So, oops. Let's say, I don't know, 44 there. And let's say well, we have the 20 there, but I might as well add a distance on this one. Let's say from there to there is 8.5, just to be different. Okay, so I don't know. I think I have one or two edges that still don't have distance on them, but we're not using those edges, so I think we're good to go. So at any rate, so where were we? We were at 30.6 by the time we got here. So now that's 74.6, 94.6, 104, 106.6. So it looks like the total distance of that path. Now let me do it this way. If I added correctly, 106.6 for that purple highlighted path, right? And let me zoom out a little bit so that I can get everything in there. Okay. All right, so, but that's one path. Is that the shortest? I would suspect probably not, because we have this particularly short edge of 0.1 kilometer, which is almost zero compared to everything else. The smallest one we have is 2 kilometers, so that's 20 times bigger than 0.1 kilometers. Probably including that 0.1 kilometer would be a lot shorter. In fact, but it would depend on, if we could even complete an entire cycle, because if we went there, then we might have to go to the 20 and then around to the 6. So that's a 20 and an 8.5. Is that as much as the 10 and the 13? So maybe not. Maybe this 0.1 kilometer edge would ultimately give us a shorter path, but it might force us to include longer edges that we really don't want. Seems pretty likely that we want to avoid the really big edges like 88 and 99, especially with so many much shorter edges. But once again, those edges, maybe taking one of those really long edges gives us a chance to take advantage of a lot of really short edges that we wouldn't have gotten to take advantage of going a different way. So you can never absolutely be sure that the longest edge or the short has to be excluded, or that the shortest edge has to be included. But as a general rule, you want to try and get as many short edges, as many low-cost edges as you can, right? Now, one thing to notice about this graph is that it's not Euclidean. Remember, Euclidean basically means that the distances make some kind of sense, like they would be kind of physically possible on a two-dimensional surface of some kind. So this graph is not Euclidean. It's probably not planar. I don't know if we could rearrange the edges in a way that, nodes and edges in a way that all of these could get on there without crossing. So it's probably not planar, and probably not Euclidean. I mean, if we just think about this 99, this 100-kilometer edge right here, that would be, on the surface of the Earth, it would be impossible to have 100 kilometers from this point to this point, and then but have this other route that goes through other points that only adds up to, let's see, 1.6 and 4. So that's not even 10 kilometers if we go around here. So the path that I actually took, the purple path, that only takes 10 kilometers to go from 0 to, which node is that? I kind of have it covered up. That's node. Wonder if I can... it doesn't want to let me bring it to front. This is where I should start using a more sophisticated drawing program for this kind of stuff, because OneNote's drawing tools are handy in a pinch, but not always the easiest to work with. At any rate, you know I'm talking about the node that I'm pointing at, whatever number that happened to be. I think we have 0, 1, 2, 3. I think that's node 4. Yeah, that's node 4. So going from 0 to 4 directly is 100 kilometers somehow, but going this other route through other cities or whatever they are only takes 10 kilometers. That doesn't make sense unless, I don't know, there's a really, like, the only way to go from 0 to 4 is through an underground tunnel that has lots of twisting and turning and stuff like that. But it doesn't really make a lot of physical sense. Now, if we're talking about monetary costs or tunnels that twist and turn, yeah, then that's possible. So solving the traveling salesman problem on different kinds of graphs, whether the graph is Euclidean or planar, or could be any arbitrary graph such as this, whether it's a complete graph where every edge has a finite cost or some edges don't have costs. All of those can be interesting cases. And depending on what assumptions you can make on your graph, it may actually be easier to solve the traveling salesman problem. Let me go ahead, just to give you an idea of that, let me copy this graph again. I think copying it from here will be the best bet. And get the formatting. Okay, so let's look at this graph again now, and actually we may want to change the numbers. Let's actually make it more realistic, right? And this is where a really good drawing tool, where if I could grab those nodes and start moving them around, I really should start using that when I do these lectures with you guys. Something to think about for next time I teach this class, I guess. But at any rate, so let's make it more realistic. Let's say the direct path there is like only 3 kilometers or something, right? And let's also add edges. Oops. We want to make sure we're using the right kind of pen there. And I'm going to add a few more direct lines. We're not trying to be planar, but we are trying to be Euclidean. So on and so forth. Then, actually, I think I'm going to just take the distances out. Let's assume... say, let's take the distances out if it lets me select them. And let's just say the distances here would be the actual physical distances between these points. because that would be Euclidean. That would be like geometry. Oops. There we go. And get rid of that one, and good. All right, so to clarify what I'm saying, suppose the distances, the costs, are the actual distances as drawn. That would mean we have a Euclidean graph. So you don't have anything weird where this can be really far from this. Like, we can't have 0 be 1,000 miles from 4, but then go from 0 to 5 in 1 mile and 5 to 4 in 2 miles. Can't have anything weird like that. If you go through at least one extra vertex to get to another vertex, that will always be a longer path than the direct path. That's basically the rule for Euclidean graphs, is that the direct path is always shorter than the longer path. But there's actually more to it, because it should obey what's called the triangle rule, which means the direct path can't be more than the sum of an indirect path that has just one extra node. So if we go from 0 to 5, and then from 5 to 4, if we take that total distance, true Euclidean graph would not allow the sum, or would not allow that total distance to be shorter than the direct distance. So you have a constraint both ways. The direct distance should not be longer than indirect distances. Actually, I should restate that the Euclidean rule just sets the triangle rule, so that the indirect distance through one other point has to be larger than the direct distance, and that goes for all three indirect distances. So whichever pair of points on a triangle you want to look at, all three of those have to obey that rule. That's the best way to think about it. And when you have Euclidean, then our normal human intuitions about finding the shortest path through all these things makes a lot of sense. You would never want to take a long jump. Let's throw in a few more edges here. You would never take one of these long jumps unless it was the only option, right? If you start at 0, you're going to go to one of the closer ones. So we go from 0 to 1, and then from there we go from 0 to 2, or from 1 maybe you want to stay close and go to 3. Now we kind of have we have a little bit of a choice to make. Do we want to go over to 2, and then we're kind of stuck with these guys as close neighbors, or do we want to go off this way and be stuck with these guys over here as our closer neighbors? So maybe we go, maybe we didn't want to go to 1 in the first place, because that's kind of far from 0. Maybe we should stay kind of in 0's neighborhood. So 0 to 5 seems to make sense. 5 to 4. Okay, well, now 3 or 7, that's kind of a choice. Not clear which one's better there for sure. Both of them kind of look okay, so I'm going to say we'd go to 7. We're kind of going around the outside. At some point, we need to pick up 3. So let's say 7, 6, 2, 1, 3. And since we're talking about realistic distances, really almost every point should be connected to every other point. So let's go ahead and throw an edge in there. So yeah, so we go 0, 5, 4, 7, 6, 2, 1, 3, 0. And I'd be willing to bet you that that's either the best path or very, very close. it's sort of thing where we can almost intuitively eyeball what the direct path, what the best path is, or something very close to it, because all of our instincts about what is closer to what and so forth apply here. A more arbitrary graph where the distances could be whatever, and they could be completely arbitrary, not obeying the triangle rule or anything like that. In those situations, it's a lot. Our intuitions no longer apply. You never know. Just because 0 and 1 are close together and 1 and 2 are close together, 0 and 2 might be really far apart. We have a really high cost between them for some reason. So you can't assume that 0 to 2 would be any good, even though 0 to 1 and 1 to 2 is really easy, or really low cost. So the number of possibilities explodes as far as what may or may not be the shortest path. Nothing is as consistent. So the Euclidean constraint on your graph or the arbitrary constraint, those again become kind of two variations on the same problem. It's the same underlying problem there, but you're just restricting what kinds of graphs you're actually going to look at. If you're only looking at Euclidean graphs, there might be algorithms that go a lot faster, because it's much easier to rule out a lot of these long distance jumps, because there's just never going to be a reason to take those. So that kind of thing is some of what we will look at in the lab. So we won't just look at solving the problem on arbitrary graphs. We'll also look at Euclidean graphs and things like that. So I just want you to be aware of that, and that we can kind of eyeball on certain kinds of graphs like Euclidean graphs. It's actually pretty easy to eyeball something that's, especially with not too many cities involved. But even if you had a large number of cities, let's say we just scattered 1,000 points onto this screen, right? And you just had 1,000 random dots, and you could just go from any dot to any other dot, and the distance between the dots is their edge cost, right? So just imagine that. Imagine you just scattered 1,000 dots here on the screen, and you're going to try and find a traveling salesman path that may not be the absolute optimal path, but you're very confident is pretty good. Well, you just start maybe up in this corner, and yeah, you just kind of bounce around, and whatever points are closest, you'd maybe make a strip going around, and then you'd go back up and down and up and down. You might leave kind of a zone up here across the top thinking, oh, that's the way I'm going to come back. And so then you just kind of up and bouncing around a little bit, short hops with up and down, 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 up and back over, or something like that. And if you did that on a bunch of random dots, again, you might not be getting the absolute best path, but you would be darn sure it would be close. It would be a few percent different from what probably the most optimal path was. And I think any of you would just do that without even ever being told what the traveling salesman problem, without ever being told about graph theory or algorithms or anything. If you just were shown a piece of paper and somebody said, connect all these dots with the shortest line possible, the shortest line you can, you would just instinctively do something that was really close. It gets a little more complicated, though, once we go to arbitrary graphs, and then the distances don't mean anything that register with our visual intuition about space and distance. So at any rate, hopefully this gives you, though, a fairly concrete idea of what the problem is we're trying to solve. We're trying to find that smallest possible distance. But when it's on an arbitrary graph, all bets are off as far as the distances between any pair of vertices. Then our intuitions of always kind of sticking to neighbors that are close by no longer necessarily makes any sense. Any arbitrary path might end up being the best path. There are still actually some intuitions. Even in that situation, there are intuitions that lead to pretty good solutions, if not the actual optimal solution, the true solution to the problem. But if you do want the true solution to the problem, you really have no choice but to consider every possible path. Actually, I should say you have some choice. There are ways of not quite checking every possible path, but let's say the brute force method. So you do have choices. There are algorithms that are better than brute force, so it's actually completely wrong to say you have no choice. But if you're going to do it brute force, the brute force method is to look at every possible path. So you'd say, well, okay, let's do 0, 1, 2, 3, 4, 5, 6, 7, back to 0. Okay, that's path number 1. Okay, let's start at 0, but just switch the last 2. So 0, 1, 2, 3, 4, 5, 7, 6, and back to 0. And again, this diagram, I don't have connections for all of those, but you can just imagine the ones that I don't have really high numbers on them, or maybe they're infinite, and if you end up with infinite for all your answers, then you know there's no solution at all. But at any rate, so we try 0, 1, 2, 3, 4, 5, 7, 6, right? So actually, let me start writing these down. So you try brute force, try all combinations, or all, well, does anybody know the technical term for what I'm getting at here? If we're talking about all possible sequences of 0 through 7, what is the technical term for that? I'm pretty sure 1 or 2 math classes would have mentioned this terminology, maybe discrete math. All right, let me go ahead and, oh, there we go. Well, when we get to the point where we're calculating how long it's going to take, factorial is going to come into it. That's not the term I was looking for. So we're trying all permutations of the vertices. So we're going to try 0, 1, 2, 3, 4, 5, 6, 7. Let me do it this way. 0, 1, 2, 3, 4, 5, 6, or 7, 6, right? 0, 1, 2, 3, 4. Let's see, so, whoops. So we swapped the 7 and the 6, so that's everything we can do starting with 0 through 5. So we have to try something different, like put 6 here, and then 5, 7, and then 0, 1, 2, 3, 4, 6, and then 7, 5. And that's everything we can do with 6 there. So 0, 1, 2, 3, somehow I left out a 4. 4, 7, 5, 6, and 0, 1, 2, 3, 4, 7, 6, 5. So now I have to try something different. We have 5, 6, and 7 in that third spot, so 0, 1, 2, 3. Now we have to try 5 here, 4, 6, 7, and so on, for however many combinations you have there. And that's going to be 8 factorial possibilities. So you're absolutely right that factorial is going to be playing a role here. So, so how many permutations? N factorial. So basically you have 8 choices of where to put the node 0 times 7 choices of where to put node 1 times 6 choices of where to put node 2, and so on and so forth. So you have n factorial computations. So, but let's think about algorithm performance. Well, the algorithm performance is you have to try every permutation. If you're doing brute force, you're going to try every permutation. And then having tried every permutation, you have to, well, for each permutation, you have to actually calculate that distance around that path. So we have n factorial permutations times the time to sum n edge costs. So you have n edge costs. Let's assume we're using normal arithmetic again. We're not using big integers, so we don't have to worry about that we might have big integers associated with our edge costs. We just have normal longs or floating point values, and we're going to assume that we're not going to let it get so huge that we need big integers or big decimals or anything like that for our numerical values. So in this case, so we have n factorial permutations, and the time to sum, and when we need to sum n edge costs, so that's just going to take n steps. That's n additions you have to make. So you're going to have you're going to basically have n times n factorial. So our order of growth of runtime, t of n, is going to be tilde n times n factorial, which is really might as well be n factorial. In fact, we might recognize that even though we're talking brute force, we might say, okay, well, we know we can stick with the same start end, right? So we won't actually move our initial vertex, so we'll never try 0 in another place, because as soon as we're trying 0 in a different position, all we're really doing is changing what our starting and ending node is, and we said earlier that it doesn't really matter what your starting and ending node is. So if that's the case, then it's really n minus 1 factorial, different combinations, because 0 is always stuck in the same place. So we have one choice where node 0 goes. Then we have we have n minus 1 factorial choices where the other nodes go in the sequence. So then we have to do a sum of n edge costs, but we have n minus 1 factorial combinations, right? So we actually do end up with n times n minus 1 factorial, but what is that? That's just n factorial. So we ultimately end up with just n factorial for a reasonable brute force. So there's brute force, and then there's just stupid brute force. So sometimes things are obvious enough that you don't want to try every permutation when you can always stick with one thing in one spot. So that at least cuts your number of permutations down by a factor of n. Still going to be a huge number if n is very big at all, but at any rate, but you still have to do the extra. You have to actually calculate that sum, and so typically you're going to have n factorial steps in your brute force algorithm. There are a few shortcuts. Can anybody out there think of anything that might be a way to rule out, just some really obvious ways to rule out some of the combinations we're going to look at? And again, we're talking an undirected graph, so the direction you go doesn't matter. All right, let me toss this out. So let's think about the path 0, 1, 2, 3, 4, 5, 6, 7. And I just want to note then back to 0. Right, because you always come back around from 7 to 0, right? So now look at the path 0, 7, 6, 5, 4, 3, 2, 1. And back to 0. Would those have the same distance or not? Actually, that's an excellent point, Michael. And that was the point I was making, that it doesn't matter what your starting node is. So I was actually already ruling out the rotations when I said keep your starting point always, let your starting point always be 0. ABC, BCA equals CAB. Not that one, that's not quite right. So ABC and oh no, okay, yeah, you are just doing rotations there, right? So those rotations would all be the same. I thought I was seeing where it wasn't a rotation. But yeah, so these two paths here, well, so rotations absolutely correct. So let me go ahead and throw that in here. So rotations of same path are all same distance. And just let me add a noted earlier by saying choice of starting node doesn't matter. So we can keep 0 as always being the starting node, and that avoids doing any rotations, because a rotation of a no node would stay in the same place in a rotation. So if you rotated this path, for example, that would mean 0 would have to shift to one of the other positions, and then these things would come around the other side. So by always making node 0 your starting and ending path, you avoid duplicate rotations, rotations that are essentially the same path. So all rotations are the same path. So that's already included in the n factorial over here. Now, if you recognize that reversing a path is not the same as rotating it. If you reverse a path, that also can avoid, I'd say that would also give you the exact same distance in an undirected graph. If it was a directed graph, these are the same. So reverse path, same distance. And that's because we always go back to 0. So we have the step from 0 to 1 here, and our final step back to home, that's our step from 0 to 1 there. So 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 back to 0. 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 back to 0. Those are basically the same path again, if it's undirected. So reverse path is the same distance if undirected graph. Okay, so that's one shortcut that is, and the rotations are the two that are kind of most immediately obvious. You might think of one or two. Actually, at the moment, I'm not thinking of other shortcuts that I would consider obvious. There are techniques to reduce it from a factorial to an exponential. And I do mean reduce, because factorials are worse than exponentials, which we haven't really discussed, because we pretty much said once you get to exponential, it's bad. There's rarely a time that you want to run algorithms that are exponential, um, unless you're only doing them on very small versions of the problem where it's not going to take forever. Um, but a factorial, is that larger than exponential? Let's talk about that. So is a factorial larger than exponential? I've kind of already said it is, but let's think it through. So if you have n times, well, let's think of it this way. Let's compare 2 to the n, right, versus n factorial. Okay, so 2 to the n is going to equal 2 times 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 2 da 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 da. And it doesn't really matter if I choose 2 as the thing I'm taking to the exponent. It could be 10, it could be 1,000, it could be 1,000,000,000, whatever. It doesn't really matter. You're eventually going to have enough of them where here I'm going to have 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Right? And this is n factors. Times n minus 2 times n minus 1 times n, right? So you'll notice that we have the same number of factors being multiplied together, but the n factorial factors are much larger and grow all the way up to n. So if you had like 1,000,000,000 factorial, or even just 1,000 factorial or 100 factorial, you're going to get something much, much larger than 2 to the 100. And no matter what you use, what you replace the 2 with, if you get n big enough, you're going to have the same number of factors, and most of the factors are going to be bigger than whatever base you choose, if you choose a big enough n. So factorial ultimately beats out exponential and is worse. It is possible to find an exponential solution. And I'll go ahead and just give you using dynamic programming. So remember, dynamic programming basically means you save, you somehow use results from simpler or shorter versions of a problem. So one way or another, you see the problem in terms of smaller problems and you build up to the full solution. Or if you think recursively, you allow your recursive functions to one way or another retain or save previously calculated solutions. And you'll notice that if you think about going through lots of permutations, notice even just these first few permutations I'm doing here. Over and over and over again, we have the same initial path. 1, 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Right? Not until we've tried all 6 ways of doing 5, 6, and 7 at the end do I finally move 4 out, right? And there I goofed and typed a second 5 instead of a 4 there. But even there, we're still using 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And likewise, how often did we have 6 followed by 7? Or, well, 5, 6, 7. We have a 5, 6, 7 there. And, well, we don't have another one yet. But it'll show up again because, for example, eventually we'll have 4 at the end, right? And we'll have a 5, 6, 7 in there. So you'll notice that all these permutations are made up of shorter paths that we keep reusing, right? So whether it's 0, 1, 2, 3, 4 or just 0, 1, 2, or 345, 345, 345. We may not do them all in the same order, but that 345, that's going to be used in a lot of different situations. And 3, 4, 5, 6 is going to show up in a lot. Not as many, but it's going to show up in a lot. And 3, 4, 5, 6, 7 is going to show up in a lot of duplicate situations. So all those subpaths of the complete path are going to be used and reused over and over and over and over again in all of our possible permutations. If we could somehow save the results, save the lengths of those subpaths, we wouldn't have to calculate them in. And not just the subpaths, but we might have the issue of saying, well, what if we wanted to go from, we don't want to use 0, 1, 2, but I want to find the shortest path that goes from 3 to 7, but uses 4, 5, and 6 in between. So I keep 3 and 7 fixed as endpoints, and then I consider 4, 5, 6, and 4, 6, 5, and 5, 4, 6, and 4, 6, 4, and so on and so forth. And eventually I find, well, if I want to start at 3 and go to 7 and visit 4, 5, and 6 in between, once I've solved that sort of shortest path that visits all nodes in between, or a specific set of nodes in between, once I've done that, then I shouldn't have to try all those permutations of 3, 4, 5, 6, and 7 again. So if there's some kind of dynamic programming approach that can be taken, whether you do a recursive function that saves results for prior parameters or something along those lines, that can give you a way to improve the performance of your function. You can actually go from factorial, which is beyond excruciatingly bad as far as runtimes go, to just exponential, which is still horrible, but is a lot better than factorial. Now, one thing that ends up being interesting about a dynamic programming approach, you have to have a table of all those intermediate results that you don't want to have to recalculate. But and that table takes up memory. So you end up needing a very large amount of memory in order to save time. And that's often the case with algorithms. You can often find various tricks, usually using some form of dynamic programming, that improves the speed of the algorithm, but then you have to use a lot more memory. And maybe instead of running out of time, you run out of memory. So there's always trade-offs there to worry about. That's another thing we'll be looking at in the Traveling Salesman lab, is doing a dynamic programming version and seeing about just actually demonstrating that sure enough you get exponential runtimes out of that, exponential runtimes as opposed to the factorial runtimes that we see here. So that's the kind of stuff we have to look forward to. That's the Traveling Salesman problem in a nutshell. Hopefully it's pretty clear what's going on there. The brute force algorithm, let me say one last thing, and this isn't the last word. I'm going to, on Sunday we're going to be talking about this more, and by that time I will have published the lab instructions so you can actually start thinking about the lab. But the first thing you should be looking up or starting to figure out is just how would you write a program that finds all permutations of a list of numbers like this. And then you can just do the consecutive numbers, 0, 1, 2, 3, 4, 5, 6. Doesn't have to be all permutations of a string or whatever. But the idea of how to do all permutations, that's the basic structure of then the brute force algorithm that solves this problem. So that's the first thing you should start thinking about is, okay, how do I write an algorithm that can just go through all permutations of numbers from 0 to n-1 in list form, and then the only thing you have to tack on to, if you have an algorithm that can do that, the only thing you have to add into it is, okay, sum up the path length each time you come up with a new permutation, you sum up the path length for that permutation. So that is a preview of things to come with the traveling salesman problem, and I think that should wrap it up for tonight. It's been a good couple hours or so. And let me know if you have any questions out there. Looks like I've lost a bit of my audience. I don't know if it was too obvious or too boring, or if people are just too busy with Thanksgiving coming up or whatnot, but that's why we have the videos. So at any rate, if you don't have any questions, just give me a thumbs up or something, and that'll be good night. All right. Thank you as usual, and I'll see y'all. Hopefully, I'll see y'all next Sunday. If you're not too tired from returning from wherever you go to for Thanksgiving. If you have a long drive or trip ahead of you, and you're going to be on that trip coming home Sunday, most likely. But I will still plan on doing the live stream them, because I want to make sure you guys have as much prep as possible on the traveling salesman problem. So do watch for the instructions to go up, so if you're bored over the break, you can get a head start on it. And that's it. Good night.